and he is also the current holder of a very prestigious Canadian research chair position, where he doesn't actually, he gets all the money and doesn't have to do all the teaching. So it's a dream job for most of us anyway. And he got his degrees from University of Annaba in Algeria, and the institute, the National Institute, Polytechnical Institute of Lorraine in France. And it's a pleasure to have you. He's, of course, obviously his interests are in imaging and computer vision and pattern recognition. It's a pleasure to have you here. Thank you for coming.
Thank you, Hamid. First of all, I have to thank Hamid to give me the opportunity to be here and to give my talk. Thank you for you to be here to listen for me. Then, first of all, I am French speaking, and then I am not too fluent in English. Then my slides, there is one part in English, but written with French style, and the other part is in the international language. The international language, the formula. This is understood by all people. Okay? Then I try to give a talk about the management of image collection, or more generally management of data. I will explain why I am interested in this project of this kind of work. Okay, I will talk about the content-based image management, and then for that I will make clear some underlying problems, and also what is the need, the user need. This is very, very important because we are building technologies for the users, and then we have to understand what is the user need and taking into account the user specificities. Then we work a lot on this problem, and we propose some approach for different underlying problems. I will focus on one specific problem today, which is which I call the long-term need, and more specifically the information suggestion. I will explain what is the information suggestion. This is a well-known problem in for example, information science, but the problem is not so known for the image processing and computer vision community, and we start working on, and we have some result about that. But for the information management, usually we need data modeling, and right now the suitable models are coming from statistics. And then for this problem, I will propose or will provide in fact some statistical models that can be used to manage information. Okay. Hamid introduced me. I have a team. I have one postdoctoral fellow, 5 PhD, and 10 master students. And we are working right now, working on visual information management, because there is a lot of data that has been generated in the world, and then we need to manage the data. Especially worked a lot in CBR, content-based image retrieval, collection organization, and right now this is a new CBS, or the content-based image suggestion. This is a word that we introduce ourselves, and also the adaptation of visual documents. Also, statistical models. We work a lot, and we continue working on statistical models. This means the estimation, okay, the statistical model estimation, more specifically the mixture estimation, feature selection, and high-dimensional data, supervised learning, and so on. And also, I'm so interested myself to the problem of especially physics-based image processing, how to use physics models in image processing, and we are working on especially on variational problems, partial differential equation problems, and color. This is in optical images, or in also in SAR. This means reader images. Okay, this is what we are working on right now. Okay, I will explain what's really what I mean by the content-based image management, and why we want to work, why we work on that problem. Okay, there is a huge amount of data that is generated every day. Okay, well, we got some statistics in 2003. 5 million of giga were new. This is a new data. What was built in billion? Yes. This means every people in the world. Okay, in 2003, they provide new data 1 gig. Okay, and this is a very huge quantity of data. I am not talking about the data that are available. This is a new. Okay, and most of the data are travel by the networks. Okay, then we need to access. To reuse this data. This means we need to store this data, we need to access this data, and the data here can be text, images, sound, videos, and so on. Okay, and the most great part of data are images, sound, and videos. This means non-textual data. Then we need to manage. Okay, we have a lot of technologies that are available for textual data. For example, we have Google, we have Yahoo, and other technologies, similar technologies. However, for image, sound, and videos, we need technologies. Why? Because when the quantity of the data increases, the probability to find the right data, the data that interests us, decreases strongly. Okay, I know some people in Montreal that spend 4 days to find one image in marketing. Okay, there's a guy working in marketing and they need some images. There is available collection and they spend 4 days. Then this is why we need to find methodologies, approaches, and then technologies to efficiently manage the data. As explained, we have Yahoo, Google, and so on, but these technologies need upgrading. Why? Because they are the first goal of these technologies is text. They are strong to handle text. However, for images, for non-textual data, how it works, then, for example, Google take images and then put keywords, and then we convert the image to the text, and then we use the text. The text is used. How it is converted? The conversion between image and text is done, usually is done manually. Okay. Okay, this is why it is important. Okay, is the sorry here. Okay. As I explained, that the available technologies that we use are based on a text. However, the visual content is not used. For example, here I take a Google and try to find God. Okay, what is God? Okay, and I find all these images. As you see, this is the first ranked images as God. Well, is it okay or not? This is not my business. Here, there is some people that identify this picture as God. Okay, and this means that then the metadata here this is true or not. We can, from image point of view, from visual content. Okay, this is, I don't know what is a God, and then I am not able to represent it in image or to take a picture. However, from a conceptual semantic point of view, or this is, I have no idea. It can be or not. This is God for some. I'm sure this is some man that elected the woman as God. Okay, but this is. Then the management criteria right now are usually based on metadata. Metadata, this means text or any kind of information that come from outside the visual document. Okay. But since people are working on, there is some background and image, digital imaging, and then we can think to use also visual content. Okay, this means the information that can be extracted from image or from video. Okay, this is, for example, when I show the technology that we have to people, okay, why you find this? Because this object and this object is the same. And people, however, as we are used to work with text, usually we think about objects and concepts. I would like to find the image that contain such objects or such concepts. However, what we know from image processing and computer vision point of view, it's very, very difficult to give a full interpretation of images or of collection of images. Okay, I remember when I started in image processing in 1880. Yes, 80. Okay, when I started, then, okay, we think that we can build a computer vision system of mobile robot that can move in the city and recognize all people, all cars, and all trees. But we know that right now we know this is very, very difficult, and the problem is approached differently. Then it is very difficult to have a full interpretation of a collection of images or videos for general purpose. Okay, then what people do is just to, as we are not able to give the full interpretation, then just we compute, we estimate from the images some visual features, usually are low-level features, and these features are used to retrieve or to manage the collection, okay? Or sometimes you use concepts, but we are able just to use simple concepts, some specific objects, for example, some specific man-made objects that can be used, okay? Then, why? Then, here we have some problems. There is other problems, okay? The other problems, for example, if we are managing data or using a numeral or using text, we can define this kind of relation, okay? Then we are able to rank element. However, if you are using other kind of information like information coming from image, it is very difficult to use this. We cannot use this relation, okay? You cannot tell that this texture is less than that texture, or this texture is equal to such a texture, because we have, this is first, we have some representation, the representation of data are different, and second, also we have some other knowledge, for example, knowledge coming from visual perception or from the cognitive science cannot be, we cannot use this kind of relation to handle this kind of knowledge. Okay, then how to find one image, for example, repair one image, this image resembles to this image. However, if I extract texture from here and texture from here and I compare, I will, the two textures are not equal, okay? Then the similarity was defined. The similarity is very, very complex concept, okay? The definition, the first definition that have been used from cognitive science is the a definition based on sets theory, okay? That if I have to compare two concepts A and B, I have to consider that the concepts are sets, and then I will use the intersection, this is the common feature, and also the differences between the two sets. This is Tversky theory that allow to write this equation, okay? Then here, we have then, instead of using this kind of relation, people are using this kind of concepts to compare videos or to compare image. A and B here usually are, we use features. This can be global features, local features, sometimes some concepts or metadata. That all this kind of information can be put and in this kind of similarity definition, okay? Also, we have another problem is the large, the large collections. For small collection, as I have a friend that tell that for any retrieval system, you can find a small set of data that it perform very well, okay? However, if you take for text, for example, we are Right now we have technology such as Google that work at very, very large scale collection. However, for the use of information coming from image processing, image processing and computer vision, we are not ready able to use this kind of features in large scale, large collections. But also there is time, if you have a larger collection, then you would like to retrieve an image, then you have to compare with all the images, and then you will spend a lot of time. Then we need to organize the collection, find some organization, and then if I have a given image, I go directly to the part that, to the sub-collection that, that contains similar images. Okay, then we have here the organization of collection. Okay, as I talk about the user is a neophyte in image processing and data analysis. We cannot, okay, the user can, any people, they have no idea what is the contrast, what is the texture, and what is the curvature and variance, and this kind of things, and also some concepts of data analysis. And also, the user have some habit, equipment. Right now, for example, we have telephone, PDA, PC, and so on. People can move a lot. People belong to social groups, professional groups, and so on. Religious groups. Also, people have some perception specificities, and for example, visual impairments. Also, the people have long-term and short-term need. Short-term need, then this is a reactive, usually can be, the answer can be the reactive technology, such as Google. If I have a need, I ask Google, I have a question to Google, then I ask the question, and therefore I obtain the answer. Okay, this means I have a need right now, I ask the technology, and I query the technology, and then I will have the answer. The long-term need is assume that there is some technology or some people that know me, and then they know exactly what's my need tomorrow, what's my need at home, what's my need at school, what's my need in all contexts. Okay. And then what I mean by the management, if I take the underlying problems that I have tackled, then we have storage, localization, suggestion, adaptation, and updating. Adaptation because we move, because we have some equipment, because I have my perception specificities, and so on. Okay. Okay, there is also human and the problems of human-machine interaction. Okay, right now, how things, for example, for short-term need, we use as example when we query the technology, the image, text, or sketch. Okay. Okay, this is here. I showed just this is collection, but the collection is this is a sample of images coming from a collection, and we take the collection and we build a summary of the collection here, okay, which is a classification problem, as we will explain. Okay, what's the scheme of general information management system? We have a user. The user have some interface. This means have some thick machine here, which can be a PC, telephone, or any other device. They have to make a query. The query is analyzed. We extract information from here. Then we have the collection. This can be a structured collection or not, like internet, for example. And then the user can retrieve similar documents to the documents in the query, browsing, updating, and so on. And when we pick here or retrieve some documents, we need to adapt documents as function depending on the device, on the user, the location, the network. And this is the general schema of the information management and the underlying problems. Okay, we have problems like evaluation, user behavior, impacts, and so on. Okay, for the suggestion here, what I would like to explain more is then we have a collection of data. Okay, this can be images, users, context, networks, and so on. And then we predict, okay, the data that can be, can interest the user given all the attributes, different attributes of the user, such as devices, network, and so on, okay? Okay, sorry, this is CBR, have nothing to do here. Okay, now, sorry. Okay, the work of the suggestion is completed by one PhD candidate, Sabri Boutemjet. He's working specifically on the suggestion model and try to build a suggestion model for visual documents. The work is based, we are using some algorithm and concept that we developed before that are linked to the mixture estimation, the mixture of probability density function estimation. The mixture of the RISLI has been studied by one of my previous PhD student, Nizar Bougila, who is right now assistant professor of Concordia University. There is one student, I think, from here, supervised by Hamid. He is in the same department. Okay, the work that I will propose here is published in some journals and some conferences. For example, we have one paper will appear in IEEE Transaction on Multimedia, and there is a lot of papers, for example, in NIPS, ISHKAI, and this kind of conferences. And also there is for statistical tools are published in many other journals like PAMI, IEEE, PAMI, IEEE image processing, and so on. Okay, then, okay. Sorry. Okay, then we give the name to this kind of problematics. We name it content-based image suggestion. Okay, why? Because, well, usually in information science, this is named information filtering, okay? And since in image processing community and computer vision community now use the word content-based image retrieval, we use a parallel to content-based image retrieval and named it content-based image suggestion, okay? Content-based image retrieval, the goal is to take into account the short-term need of the user. The content-based image suggestion is to take into account the long-term need. Both needs can be combined. For example, to suggest info data, I can use the content-based image retrieval system for the acquisition of knowledge about, for example, users. This can be one solution to such problem, okay? What's the basic idea here? If you have, for example, 2 users and we know these users, the profile of the need of these users and some attributes about this, such users. For example, both users like this kind of motorcycles, okay? And then they have a lot of common objects that they consume, okay? And these objects are similar. Then this user, for example, buy a camera. We deduce that the second user will buy the camera. Then we have to suggest the camera to the second user. This means here, users are clustered, grouped in different groups, and this can be based on preferences of users, visual features, or textual features, the metadata, and so on, okay? The CBS, every people have seen the CBS before, the windows that pop up in your computer. Do you like that? Now? I have to stop working on. Okay, CBS, okay, right now the CBS models, okay, early the CBS models is, okay, our contribution, main contribution is to add visual information and to show that visual information is, has added value. Okay, then if you make a suggestion with visual information and suggestion without visual information, with visual information the suggestion will be more accurate. Then you have less windows that pop up in your computer. Okay? Okay, also we would like to add the context. Okay, what is the context? The context is linked to the user. Okay, this means what do you to separate the life of the user on different parts, the work, the house, and the city, and with the groups, with such a group, and so on. Okay, this is the context. It can also include the telecommunication cost. It can include the device specificities that the user is using, and so on. Okay. Then, why? Because our need depend on the in our context. At my office, I haven't the same need as at my home. Okay, then this is the context what we would like to add, visual information. Also, here is we have the suggestion criteria involve a lot of data, and this data from if we put this data in some space, we have a high dimensional space, okay, and how to modelize and handle data in high dimensional space. And also we see the suggestion problem as is based on learning and how to do the supervised learning, especially the estimation of statistical model. This means the number of populations and the future selection and extraction. Okay, then we name this model as here VCFMM, as I will explain. Okay, right now I will give some formalism for this problem. What I have to suggest, I have users, okay, I have visual documents, I have context, and as you know that the suggestion or recommendation is based usually on rating, okay? Then you have document, these documents have received some rating, okay? And I have a set of rating. This can be yes or no, for example, or we can use another scale, for example, rating between 1 and 5. 1, I don't like it, but 5, I like it, okay? Okay, here, okay, visual documents here are features. Each document is represented by a set of features. This can be any information that can be estimated or feature that can be estimated from an image or a video. Okay, that can be a local descriptor, global descriptor. It can be sketch, skeleton, and so on. Okay, and then the curves, for example, that you represent in space by, if I understand, on manifold by point, it can be very, very. This is why I was very, very interested in. Okay. Then what we need, then we have some data here. The data are the user, the context, the visual document, the rating, and we would like to make some inferences or prediction. Okay, I will explain. From what's the dependence between these variables? We would like to predict the rating for a document. If the rating is high, we will suggest the document. Otherwise, we will not suggest the document. The rating depends on the user class, the user and the context classes, and also document classes. Okay, why we use the concept of classes here? Why? To handle a new data. For example, if the user is not noun, how I can suggest to this user? Then if the user resembles to another user, other users that are in a given cluster, then I can suggest to this user the same information as explained before on the example of motorcycles. Okay, this is the same thing for documents. Okay, then the documents are grouped, and this is the grouping allow to handle new documents and new users. Okay, what I mentioned here is we take the users context and ratings as numerals. Okay, then I have the user one. The user one can be a woman where the age is within intervals and so on. Okay, I encode this here, represent this by numerals. That from statistical point of view, I have here categorical data, and this is here are textures, colors, and so on, and this is donc real data. Then in the model here, I will handle categorical data that are discrete and with other data that are not. Then a part of the model is for discrete, how to modelize discrete data. Okay. Well, how we can see that? We see that as a generative model, statistical model. What I mean by generative statistical model, I have the user, I have the context, the document, and the rating. I consider this as a space. Okay, I would like to provide a model for this space. Okay, the model for this space, as we see before, we have two hidden variables, which is the user context class and the document cluster. Okay, then this is straightforward. If we decide to use generative model, then this is can be we introduce here hidden variables, and then we write this according to our graphical model. This means the dependencies between variables, and then we can, it is straightforward to write it, to decompose it to some probabilities, okay, or probability density function PDF, okay. Then the question is to find the interpretation of each of which, okay. Then here I have PZ and PC are the, as I have clusters of users and the clusters of documents, then this is the weighting for the for example, PZ here is the weight of the class numbered Z. Okay, this is give me the we call this the mixing parameter, the weight of the cluster. Here, and this is usually in mixture domain are computed. The computation is straightforward. Okay, I will show that later. Okay, this is what's here. This is the P, U, E, and Z are the probability density function of the user and the context. This means I have a user Jack as user, and in the context one, Jack in the context 2, Jack in the context 3, and then this is, as I am using categorical data, this is straightforward. That is a multinomial distribution. Okay, just from the fact that I am using numbers to represent my class, my users, and my contexts. But however, here, if I have to change mind, and I would include directly here, for example, the specificities of the attribute of the user, then I can change this distribution by another. This here, this distribution, P, R, Z, C, is here the rating. Then I have a cluster of of documents and cluster of users, and I have a rating between, and I model the rating here given the hidden variables. Okay, since the rating is numbers, for example, between if 0, 1, this is will Bernoulli distribution, but here R can be, for example, between 1 and 5, and then we can use a multinomial distribution. Okay. Well, I will explain more the PVC. This means the a cluster of document. Okay, the cluster of document. Okay, we assume here we make assumption it is a generalized directly distribution. Okay, this is usually in mixture on this kind of problem we use Gaussian. Okay, why we are not using Gaussian here? Because first of all, because we are working since a few years on this distribution. Why? Because we are interested in now the modeling of now Gaussian data. Okay, the Gaussian is a very interesting function. We have a lot of knowledge about this function, and okay. However, in real life, how many data are really Gaussian? This is, well, some data can be Gaussian. If you take a SAR images which is formed by adding some echoes, okay, if the number of echoes is high, then we have the limit central limit theorem, okay? Then it will be a Gaussian. However, this is not the process, generating process that is used everywhere, okay? Then, since we are interested in modeling no Gaussian data, then we introduce and we work a lot in what we call the Dirichlet-Liouville family of distribution. Okay, what's this distribution? If you take a random vector, okay, then the random vector is a Dirichlet, follow the Dirichlet distribution with if the density can be written such in this form. Okay, what I can give you as interpretation here, this is a polynomial. Okay, there is no exponential here. This is a polynomial. You have x here, a v here, and 1 minus v here. This is really a polynomial. In one dimension, we call this distribution a beta distribution, and then high dimension, we call this a Dirichlet distribution. Okay, then the Dirichlet distribution or the beta distribution is the one term of a polynomial of degree n. Okay, then what's the benefits here? The benefits, well, this distribution have a compact support. It is defined, for the variables are defined between 0 and 1, okay? This means if you use, for example, the moment to estimate when we if we need to estimate the moment, it is very, very accurate, okay? For example, for Gaussian, you have infinite support, and then to estimate, you have to cut the support, and then you have some trouble or inaccuracy with that. Then it can be symmetric distribution. You can handle tails, okay? Because it can be asymmetric left, asymmetric right, and so on. Then I take a lot of possible shapes, okay? I can explain things differently. For example, if the shape of a distribution is defined by the third and fourth moment, okay? The Gaussian have the third moment is 0 and the fourth moment is 3. Then it is if you take the space of the third and fourth moment, the Gaussian is point. The Dirichlet is an area, okay, that it will take a huge infinite possible forms. Then it is very, very flexible to fit data. Okay, for example, if you have this histogram, then you put Dirichlet on, you will have the function, and the function here we have 4 population. The population can be asymmetric left, right, symmetric, no problem. Then this is very, very interesting. Okay, another property is it is very suitable for high dimensional data modeling. Well, before I tell you why, the high dimensional, we have a lot of problems with high dimensional data, okay? Why? Because, okay, first of all, okay, if I take, for example, I have a space of 100 or 1000 dimension, okay, and when we make some processing or some decision inside using this space, we can have a lot of wrong decision, okay? Then we have some problems doing classification, prediction, or clustering in such space, okay? Why? Because we have first, we know some factors. For example, we can make a lot of mistakes with computation, with the accuracy of computation. Assume that you have a Gaussian, okay? And in the Gaussian, multidimensional Gaussian, you have exponential minus the Mahalanobis distance, okay? Assume you are in 1,000 space, dimension space, okay? The dimension of the space is 1,000, okay? Then the distance, Mahalanobis distance will be huge. Exponential minus some huge number will be, in practice, 0, okay? And we are not able to compute. For example, if you have data, I would like to model cluster, okay, using a normal law or Gaussian, you cannot do that more than 11, 12 dimension. If you have a space in 20 dimension, you cannot do that, okay? We have another problem, which is what we call the non-informative clusters, okay? There is some clusters that are not interesting. I will explain this. This means there is some data which we cannot put in a given class, okay? It's difficult to put in cluster, okay? What we write here, independent of class labels, okay? I explain, for example, the Gaussian. For the Gaussian, we cannot, for Gaussian with full covariance, we cannot use it on this kind of machine, okay, on PC machine, more than 12 or 13 dimension, okay? Or if you take data, for example, for content-based image retrieval, object classification, and so on, you have 400 dimension, okay? If you go to the company not far from here and you ask for the client file, you have 400. This is the client file is a space of 400 dimension or 300 dimension. Okay, how we can do that? But first of all, we can assume that the covariance of the Gaussian is diagonal, okay? This means you can split the dimension work on each dimension alone, okay? But you are doing assumption that there is no correlation between different axes, okay? Different dimensions. This is a strong assumption, okay? Another approach is you take your space, okay? You project your space in a space of small dimension, and then you work in space on small dimension, okay? Then, for example, you have a space of 400 dimension. Then you project it in 10 dimension, and you work on. Okay, from the projection, this is what we call the PCE, for example, l'analyse en composante principal component analysis. Okay, for example, ECN and this kind of tools. The problem with such tools, okay, I'm here invited by a group that work on geometry and topology. If you have your data have some topological properties in the space of 400, when you project, are you sure that you will keep the geometrical and topological properties? Okay, for example, assume that you have some cycle in your data, and when you project, you are not sure to keep the cycle. Okay, this is the projection. Then it's okay, but we don't know what we are doing when we project. Okay, I'm talking about projection in PCA projection and this kind of tools. Okay, then it works, but I don't know why. Okay. Now what we did, okay, the Dirichlet distribution has a nice property that if you take this geometric, this transformation of data, I have a V space, and they transform it to a new space, which we call it here, which is noted here, X space. According to this transformation, you decorrelate the data, okay? And your Dirichlet distribution can be written as the product of the beta distribution. This means is separable. Okay, separable. Okay, is separable. This means you can work on each axis alone. Okay, and this we prove that this distribution allow to write this transformation allow us to allow us to work on each axis separately. Since I can work on each axis separately, I can put 100,000 axes, and I have no problem to work with each one separately, depending on what I am doing. Then, with the Dirichlet distribution using this space transformation, okay, I can work on each axis alone. Okay. And what is interesting, we have the same parameters. The parameters does not change. Look here. This is the product of beta distribution, 1D distribution. With each beta distribution have these parameters, are exactly the parameter of the Dirichlet here. Exact. Then this is a nice properties that allow us to modelize data in any high dimensional space without trouble. Okay, we are not using projection here. Okay. Then, okay. Right now I will explain again here. I tell you that if you have a dimension, you have some space. Okay, you have some data that you cannot put in a given cluster. Okay, that we cannot put in a cluster. Okay, we call this from Bayesian point of view, or the school of thinking, this is non-informative data. Okay, non-informative data, I will explain here. If you have, this is three-dimensional space, we built it, we display it here by projecting the data in each subspace, two-dimensional subspace, and also one-dimensional subspace. For example, the feature 1, this is the histogram of the feature 1, the histogram of feature 2, and the histogram of the feature 3. We have two population here, and one population here. We conclude that this feature is non-informative. Okay. What is interesting here? We would like to remove clusters that are non-informative. Okay. How? Okay. If a feature, okay, is this feature can be inside this and inside this. This is common. Then we throw it. Okay. There is, okay, I will explain. I don't know if people are used with some statistical concepts or not. Okay, if you take a distance, okay, feature is non-informative or irrelevant if the distance between two is 0, but this is not the distance, the Kullback divergence is equal to 0. This means if I have feature in this cluster and feature in this cluster that are exactly the same feature. Okay, then I am not, I can't cluster this data. Then we would like to remove these clusters. We call this the feature selection. This is an approach of feature selection. Feature selection, people that project using PCA are talking about feature selection. This is variance criteria. Here, the criteria is the common feature between clusters. Okay. Then if you take, from clustering point of view, I assume that I have complete data here. If I take pictures, for example, a lot of pictures of some object, okay, but I am focused just on the object. I have huge pictures, okay. Then I have if I look for that from object point of view or from cluster point of view, I will have the cluster. For example, assume that my object, there is just one cluster. I have one cluster of the object and I have other thing. But I'm changing, okay, I take the car inside the water, the car on the road, the car on the mountain, the car on, then the background will change a lot. Okay, then any object in we can assume that any object can be in the background. Then here, I will have approximately two clusters. The class cluster and another cluster which contain everything. This is trash, okay? Okay, what we call the bag of, this is a bag, okay? And then here I will have, but every object is likely to be will be found here. Then here I will have the cluster of my object and uniform distribution here, because any object can be here. Okay, then this is the idea we are using. If I take a document for one, okay, it can be some here. The cluster will be a part of the objects, and the other part is what I call the trash. Okay, and here there is some proportion of there is a mixing parameter. Okay, well, the proportion of this this part of the cluster and this part of the cluster. This is really intuitively what and the selection here consists to remove this part from data. Okay, this is the trash. This is the part that is not interesting according to our definition of relevance. Okay, and then just we will pick the part, the car. Okay, this is we can write. This is we have the mathematical writing of all that. I am giving just the part, the intuitive part explanation. Okay, my space, okay, generative space now, I have all the densities, but however here, my document, the feature of document are written in this form here. And this can be done in high dimensional space because we can work on each dimension alone. And I have one part of which is interesting, which is relevant, and the part of irrelevance. Okay, and what we would like right now, this is the graphical model. Okay, we introduce here some parameters because here we have the epsilons, for example. Okay, what we need now in our generative model is to find all the parameters. Here, this is multinomial, multinomial. This is Dirichlet. Okay, this is here. These parts are Dirichlet distributions. Okay, but we will have relevant part and irrelevant part. Okay. Okay. Then we need to estimate this parameter. I will introduce how to estimate this parameter. Okay. In mixture, this is the old problem of mixture. If you have this is a mixture, I would like to estimate the densities. You need to find the number of population. What we have here, we have two parameters. Okay, the number of clusters. We have the clusters for documents and the cluster for the user and the context. This is mean here. This is we call this the order of the model or the number of clusters. We have both here, not one as usual. Okay. Then we would like we have to estimate all the parameters and also the number of clusters. Okay. To estimate parameters here, if the parameters are real, we have to, for example, you can use the maximum likelihood and or the M algorithm, and then I will obtain that. Okay, we will obtain the parameters. However, how to obtain the number of clusters? This is what we call the unsupervised learning. Okay, I will explain how we obtain the number of parameters and also how we obtained the parameters. Okay. Okay. What we have is the theta is all the parameters of all distribution we have. Okay, Dirichlet and multinomial for each part of the distribution. The number of distribution here. Okay. As I explained, usually we can use the maximum likelihood. However, the maximum likelihood cannot give the number of population. Then what we call also the statistical model, and also the maximum likelihood. Usually, the the maximum is reached when we take each sample as cluster. Okay, then we have to put constraints from really optimization point of view. Okay, there is some criteria that are known to estimate the number of population. You have, for example, the peak. Okay, you have the MDL. Okay, minimum description length and so on. Okay, there is some criteria that are used. We work a lot since I think now at least 7 or 8 years. We are working on one criteria, what we call the minimum message length. This criteria was developed by a team, statistician team in Australia. But we work a lot on. Why? Because I like this. I like this criteria. It comes from information theory. Okay, information theory. This means really it can be explained by information theory principle. Why? Because the goal, the idea comes from the following scenario. You have two people that communicate together. You have one people that will send a message to another people. Then they take data, they encode the data, and then they send the data. Okay. The goal here, the second user, okay, or second people will decode the message and use it. Okay. The goal is to have the minimum length of the message. Okay, and this is from Shannon theory. This can be written as probability, using probability, and it can be seen as maximizing the posterior probability. Okay, and by the maximum probability can be seen, okay, or approximate by this formula, what we call the MML. Okay, it can be seen also the second order Taylor of the posterior probability. Okay, why it is interesting? Because it regularizes the posterior probability. In this formula, what we have the priors. This is according to in the bias thinking of school, it is the prior knowledge. You have the number of parameters, you have the likelihood, and also you have the Fisher information. Okay, the Fisher information is not, for example, in the criteria like BIC, like MDL. You haven't this information. But what it capped, what the Fisher information represent? It's very, very interesting. This information. This information, what's the Fisher information? Is the expectation of the Hessian matrix. Okay, the Hessian matrix. Okay. But what the Hessian matrix, usually we use it when we change variables in integrals. Do you remember that? Okay? Now you don't remember. Okay, I will explain intuitively. Okay? If I take, there is a family of distribution that have distribution have parameters. For example, the Gaussian is defined by mean and the expectation. Okay? Variance or okay. Standard deviation. Thank you. Okay, if you take these parameters, take any values, okay, these parameters, what happen? The form space. Okay, we have the mathematical demonstration proof that this space is Riemannian space. Okay, then when you would like to estimate, for example, the mean, and you are using metric, okay, for example, assume that you compute a mean as a sequence of values, okay, and you are using differentiation, for example. You are not in Euclidean space. You are, for example, on a sphere, okay, you are in sphere. Then you have to take into account the metric, okay. This is the metric, okay. Then this information, okay, I am giving the geometrical interpretation of this information. This information gives you the metric of the space on which you are working, and all the exponential family. Okay, the parameters of exponential family form Riemannian space. Okay, What we need? We have to define what's the priors, what's the information, Fisher information, the likelihood. We have to put the equivalent formula here, and we will have our criteria. Okay? Okay, I'm not giving all because this is too long. Okay, usually we assume that the parameters are independent. Otherwise, I will spend my life computing just the formula. Okay, then okay. In this case, the Hessian matrix is a block diagonal matrix. Okay, how it is computed really? This is also seen as then you take the likelihood and you compute the Hessian matrix. Then you take the norm, this norm, and you have this the Fisher information. This is a really computation problem, no more, no less. Okay, this is 3 gamma function, and forget it. It's not so important. Okay. Okay. Then you will compute the Fisher information for each parameter, and then you'll have your MML. Okay, minimum message length. We did a lot of work on the compare MML with different criteria. Until now, it is one of the best criteria. One of the worst criteria is the MDL. Okay, big is not so is a good criteria for people that are using such criteria. Okay, what we need right now, we have to estimate parameters. Okay, our parameters. This means the number of population, user population, visual document population, and the parameter of densities by minimizing the MML. Okay. This is just, I have the MML, and I take some constraints here. Why? Because I have a lot of variables that follow multinomial distribution. This means that the parameters sums to 1. I take this as constraints in my optimization problem. Then this is a constraints. We add the constraints here using Lagrange multipliers, and then just we have to derive. Okay. Then we derive. I give example here. I have my MML. I have all the constraints. We derive here with, for example, 1 of parameters, and we equal this is equal to 0, and we have to resolve. Okay. Then to find the parameter here. Okay. This can be done by as you see, you have some quantity here, which is this quantity. This quantity is the posterior probability, a prior probability which can be computed in the E-step if you are used with this kind of algorithm. Otherwise, it's really optimization problem, nonlinear optimization problem under equality constraint. This is straightforward. You compute this quantity Q here, you plug it in this formula, and you have your parameter. Okay, the last I think that I have from modeling point of view is I have modeled my space of data and of user context and so on. I will go fast. Okay. Then I have to make prediction which document I can suggest to people. Okay, I have a people and a user and a would like to suggest a document. They define what we call here the utility function. The utility function is I would like to can I suggest the document X to the user U in the context E, and this is the rating. Okay, this is defined since we have the ratings, for example, can be between 1 and 10 or 1 and 9. We will split apart what we call this rating we cannot add, and for that rating we will add. This is what here. This is the probability here of rating such that we send, and the probability of rating such that we can't suggest the document. This is the log likelihood ratio. And then what we need is to compute this, the probability to suggest and the probability to not suggest, the ratio, and this allows us to decide. Okay? Okay, this is how to compute this probability. Since we have modeled the space, we know, if you remember, we have computed this. Thus, we can deduce that. This is straightforward, okay? Sorry. Then here it is straightforward to compute that and that directly from the space, okay? Then here just we compute that. Then we compute the utility, and we decide to send or not. This we can have a binary decision, send or not send. Okay. There is some problem how to update here the diversity. Diversity is what, if I have, for example, I send a bicycle, it is not interesting to send 10 pictures of bicycle. Okay, if there is some similar document. But to maximize the diversity of document, we introduce this by changing every time when we decide to send this document, we remove all similar documents from the collection, and we update our models. And when we finish the suggestion to the user, then we put again the document inside the collection. This is how to handle the. Okay, I will give you here some result. There is 27 graduate students that participate to to our test. Then we built some system, suggestion system for telephones. Okay, and then people, we have some profile of people, and then we send images to people. We suggest each week. I think we suggest images, and then we take the feedback from people. Okay, this is a student in the laboratory or the bachelor student around us. We take the context as, for example, location and time. Location in campus, out campus, and the time weekend or weekday or weekend. Okay, we take then we take here for still image. We use correlogram for each band for RGB images, edge histogram, and shift point. For the shift, this is corner, like interest point in image. And we take here approach of dictionary, then quantification, and we built a vector of 500 dimension. Okay, for the performance, we predict the rate. Okay, we know the rate, and we compare the error with the predicted rate and the ground truth. Okay, why we did that? Because in information science, information filtering, all people use this criteria. Then referees ask us to use this criteria because there is a lot of criteria that can be used. Okay, and here we have. I will explain. There is several versions of the algorithm. Here, for example, is what you see here. This is the same thing. Here, if the this is the error, estimation error of rating. Okay, as a function here of the number of clusters of this is document clusters. Okay, and this is here for K is the this is the user cluster and document cluster, and this is the error. Then if we have few users, we have a lot of error, I think. And here, if this is the error here in the prediction, here this is the number of users and the number of class documents. We have for 4 class documents and 2 user class document, we have the less error, and this is the ground truth. Okay, I will give you other thing here. We take some algorithms and we compute the average error. Okay, we did 10 runs. Okay, this is existing algorithm here. For example, this is the same algorithm. This is the flexible mixture model developed by Jean and C and Jean. And if we add visual information, this is just the use textual information. If you use add visual information. This is the improvement, okay? And this is here if we use for the, here, this is with selection, is the same thing, but using selection here, the selection of feature, okay? Then here we use just relevant features, okay? We have an improvement. Here is we use, this is independent and this is dependent with the transformation. Then this means we are working in high dimensional space here also, but here we are using assumption that the variances, the covariance matrix is diagonal and here is not, okay? Then what can be learned here, the main thing, it's important here that by adding visual information, we improve the suggestion, okay? Okay, this is here is the same thing. Okay, this is also here to handle a new data. Here, for example, the error for each algorithm as function of the user, the number of rating by user, and here the proportion of unrated image. When the proportion of unrated images increases, then the error increases and so on. Okay, thank you. Désolé, je pense que j'ai pris beaucoup de temps.
Any questions? Yeah.
Yeah.
Yes.
What is the exact feature that you use to represent an image in your
This is what I present here.
Yeah,
Okay, quickly.
Edge histogram and the
Yes, the orientation histogram, the correlogram, and the shift.
and you said you have a clustering for the object and the background. So I don't see how you're using those features to find the object, to define the object in a certain image.
Now, we haven't explicit modeling of object. When I talk, I take this example to make clear the concept of relevant and irrelevant feature. Okay, but we are not here. We are not modeling directly the object. What we are doing, we take a feature space of 540 dimension, okay, and that we are building clusters. Okay, when we built cluster, we made a feature selection. Feature selection consists to remove irrelevant features. Okay, are removed just from the irrelevant features of visual documents. We are not doing that for user. Why? Because the user, we consider this as categorical data. Okay, then we have just numbers, the numeral, the identifier of the user. Okay, then we are not here modeling an object, another object, and then suggesting the modeled object. Okay, we are working on the whole image, not on specific objects. Okay.
Any other question? So what's the typical performance in terms of time performance?
Oh, very, very quick, because all this are about, for the modeling is did offline, okay? Then the model of future space is did offline. Then just if, for example, when you suggest, then you evaluate just this, you compute this function, okay? The model is known, the function is known, then you have just.
But you still have to go search for those, right?
No, you haven't to search, this is automatic. Then I know you, okay? For example, I decide to send you suggestion, one suggestion a week at home and one suggestion a week at work. Then just I have, for example, Monday, okay? For example, Monday, I send you a suggestion for the work. Then the computational complexity of the algorithm is to compute this formula 12. But however, the model, this means the parameters are known because this was learned before. This is very, very quick. Okay. Mm-hmm. Yes?
You draw a picture of the diagram of the
Okay.
user and the, yeah.
Diagram.
I have a question about the application actually. So for when a user they're using the taxes to send their requirement for certain information. So it seems that the retrieval or the searching is still based on taxes.
Sorry,
Is that
can you
true?
repeat, start from?
I mean, it's like you're searching in Google or
Yes.
Yahoo. You're still typing your some message or a text.
What?
to- Text to identify what you want.
Yes.
And so how do you suggest the user based on the content of image? Because the user doesn't give you any content. They gave you some word.
Oh, we
You still
assume-
have to rely on the keyword.
Yes. This is a good question. In information suggestion, we assume that there is a lot of there is some strategies to acquire information about you. Acquire information about you, okay? Then usually because you navigate internet, you can give your own information, okay? There is sometimes client in companies you have some a profile. Assume for example for telecommunication company that you are sending pictures to friends, okay? Then they know they have some profile and so on, okay? Then there is some strategies that are known, okay, and described on papers and books about how to acquire information about users. Okay, there is also volunteer that you can, for example, give yourself the information. Okay, I give you one specific. Assume that you are using a content-based image retrieval system. Okay. One system, okay? Then they have all the image that you have used before. Okay? Then you can suggest.
All right, let's thank our speaker again.
Merci.
Can we meet